So today we will learn an important topic in quantum chemistry, that is Born-Oppenheimer approximation. This is a very important approximation that we are using in quantum chemistry. We have already learned about the approximation methods, and this is very important, and you will understand why it is very important when we are going to finish this session. Okay, and it was introduced by the famous quantum physicist Max Born. This is Max Born. Max Born. Okay, this is Max Born, and this is Robert Oppenheimer. Oppenheimer. Okay, Robert Oppenheimer. And Max Born was a German physicist, and he obtained his PhD from University of Göttingen, and then he was serving in University of Göttingen for a long time. And Robert Oppenheimer was an American physicist, but he was a student of Max Born. Okay, and Max Born and Robert Oppenheimer gave a very important contributions to the world of quantum mechanics, especially in the early development of the quantum mechanics. And it was Max Born who defined what's the real meaning of the wave function, and he was a Nobel laureate as well. And Robert Oppenheimer, I already said he was an American physicist, and he was a graduate student of Max Born. And during World War II, this Oppenheimer was directed. Oppenheimer directed the Los Alamos laboratory that developed the atomic bomb. Okay, so these scientists are very important figures in the scientific world. So we are going to learn an important approximation by the teacher and student, means Max Born and Oppenheimer. Okay. And before beginning, let us go through a simple system, and this simple system is the hydrogen atom. Not hydrogen atom, hydrogen molecule. Okay, we will talk about hydrogen molecule. H2. This is a hydrogen molecule, and it has been formed by the combination of two hydrogen atoms. One hydrogen atom has a proton in it and an electron around it. The proton is the nucleus, and the electron is there around the nucleus, and there are two hydrogen atoms like that. Okay, the second hydrogen atom also has a nucleus and electron. Then these two hydrogen atoms combine to give the hydrogen molecule. Okay, so these two combine to give the hydrogen molecule. And we are going to deal with we are going to learn a little bit about the simplest molecule. This is the simplest molecule because this molecule is constituted by the two simplest atoms, that is the hydrogen atom, right? So this molecule, hydrogen molecule, actually it is a four particle system. You already know that it has two nuclei. So let me put the nuclei in the yellow color. So it has two nuclei. So this is one nucleus. So let me call this as hydrogen nucleus alpha. Okay, and this is another nucleus here. So this is hydrogen nucleus beta, and then we have two electrons also, right? So let me put the electron in the orange color. So this is the electron 1. Okay, this is electron 1. I denote this as electron 1 1, and this is electron 2, electron 2. Okay, so this is a four particle system. What kinds of interactions are there? There are several interactions. The electron interaction is there, right? Electron interaction is there. That is a repulsive interaction. Then nucleus interaction is there. Let me draw this in the white. The electron interaction is, sorry. So electron interaction is there. Then this is a repulsive interaction. Then nucleus interaction is there. That is also a repulsive interaction. Then the nucleus alpha interact with the electron 1, then nucleus alpha interact with the electron 2, right? Then nucleus beta interact with the electron 1, and nucleus beta interact with the electron 2. So these are the interactions possible here. So this is the four particle systems with so many attractive and repulsive interactions. So with this information, we can constitute the Hamiltonian for the system. So Hamiltonian, actually, you know that the Hamiltonian has the kinetic energy part and the potential energy part, right? So we have to consider the kinetic energy and the potential energy involved in this system. So when we are talking about the kinetic energy, there are kinetic energy of the nuclei. So kinetic energy of the nuclei. First, we have to talk about the kinetic energy of the nuclei. Then we have to talk about the kinetic energy of electrons, right? Then we have to talk about the potential energy. So potential energy is due to different interactions. Which are these interactions we already mentioned? Which are these interactions possible, right? The interactions between the electrons, interactions between electron and neutron, electron and proton, and the proton-proton interaction. So different interactions are possible there. So the potential energy is originated due to these interactions. So we have to talk about the potential energy due to nucleus repulsion. Potential energy due to nucleus repulsion, right? Repulsion. Then fourth, we have to talk about the potential energy due to nucleus electron attraction. Okay, and then we have to talk about the potential energy due to the electron repulsion. Electron repulsion. So we have to talk about many kinetic energy terms and potential energy terms. Then we can constitute the Hamiltonian for the system. So what will be the Hamiltonian? We can assume what will be the Hamiltonian for the system. So the Hamiltonian H cap in this case, is equal to minus h square divided by 8 pi square, right? Minus h square divided by 8 pi square m. That is the kinetic energy part. I am going to write the kinetic energy of the nucleus. Okay, so minus h square divided by 8 pi square m del alpha square. So this del alpha square, that is the Laplacian operator for the nucleus. Okay, Laplacian operator. You already know this Laplacian operator. So del alpha square minus h square divided by 8 pi square m del beta square, that is the Laplacian operator for the nucleus beta. Okay, first one was for the nucleus alpha, then this one is for the nucleus beta. And then we have to talk about the kinetic energy of the first electron and kinetic energy of the second electron. Then the operator for the final kinetic energy of the first electrons minus h square divided by 8 pi square m. Here you have to give capital M. In the first case, you have to give capital M in order to show that is the mass of the proton. Okay. And in this case, I am giving minus h square divided by 8 pi square m. That is a small m, just to indicate that is the mass of the electron. And del 1 square is the Laplacian operator for the electron 1 minus h square divided by 8 pi square m del 2 square. Okay. And these are the kinetic energy terms of the Hamiltonian operator. Then now we have to include the potential energy terms. Which are the potential energy terms? That is, first one is the potential energy due to the nucleus repulsion. So it has positive signs since it is a repulsive potential energy. So nucleus and a nucleus repulsion. Nucleus repulsion. The nucleus have the elementary charge E, that is the same charge of the electron, but it has the different sign of the charge of the electron, but the magnitude is same, right? So the nucleus interaction, that is Q1 Q2 by R. If the 2-point charges are being repelled, then the repulsive potential energy is Q1 Q2 divided by R, where R is the distance between the 2 points charges Q1 and Q2. Like that, here the two nuclei are repelling each other. Each nucleus has the charge E. Then the potential energy due to the repulsion is E into E, that is E square divided by the distance between the two nuclei, that is, we can write it as R alpha beta, alpha beta. Okay, that is R alpha beta is the distance between the two nuclei. Then we have to talk about the attractive potential energy between the nucleus and electron interaction. Okay, nucleus electron interaction. Then we have different nucleus electron interactions. So we have to write all those attractive potential energy terms. Okay, first the interaction between the nucleus alpha and the electron 1. Then it is minus E square, because that is the charge of the nucleus and the charge of the electron, that is minus E square divided by R R sorry R 1 alpha. R1 alpha means it is the distance between the electron 1 and the nucleus alpha. Okay, and next one is minus E square divided by R1 beta, R1 beta. Next one is minus E square divided by R2 alpha, 2 alpha. Then minus E square divided by R to beta. Okay, these four constitute the attractive potential energy due to the nucleus electron interaction. Now one more term is remaining, the last one, that is the potential energy due to electron repulsion. Since it is a repulsive potential energy, we can give the plus sign there, so that is E square plus E square divided by R12, where R12 is the distance between the electron 1 and the electron 2. Okay, so this is the Hamiltonian for this hydrogen molecule. Okay, now the Schrodinger wave equation. Once you have the Schrodinger wave equation, you can set up. Once you have the Hamiltonian, then you can set up the Schrodinger wave equation. The Schrodinger wave equation is the eigenvalue equation. That is, in this case, the Schrodinger wave equation is H cap. That is the Hamiltonian, which we have already written here. Okay, you already know what is H cap. We have already written here H cap. This is the Hamiltonian. What we have written here, the long expression H cap psi, that is a wave function, and psi depends upon both the position coordinates of the nucleus and the electron, right? Because we have the electron and nucleus, so it depends upon the position coordinate of the nucleus and the electron, nucleus and electron, Qn Qe, okay, Qn Qe, where Qn and Qe are the electronic and the nuclear and the electronic coordinates. Qn represent the general nuclear coordinates, and Qe represent generalized electronic coordinates. Okay, so psi is a function of both. Is equal to E, that is the eigenvalue, that is the energy of the whole system, multiplied by psi Qn Qe. Okay, so that is the Schrodinger wave equation. When we are solving the Schrodinger wave equation, we get the expression for the psi and the energy eigenvalue. Okay, now we will talk about solving the Schrodinger equation later. Just I introduced this system just to make you familiar with this system with more than one nucleus and more than one electron. Okay, and now let us suppose a system. The system has n number of nuclei and p number of electrons. The new system. A new system, we are considering a new system with the n number of nuclei. Nuclei is equal to n number of nuclei. That is number of nuclei and number of electrons. Number of electrons in this case is equal to p. So we are considering a new system with a n number of nuclei and p number of electrons. Okay, and in this case we are defining the electronic and we are defining the electronic and nuclear coordinates by the letters r and r. For example, the nuclear coordinates are denoted by r, and the electronic position coordinates are denoted by small letter r. Okay, and now we can constitute the Hamiltonian for this system. Hamiltonian. How we can constitute the Hamiltonian for the system? Just like we constituted the Hamiltonian for the hydrogen molecule, having the 2 nuclei and 2 electrons. Here we have n nuclei and p electrons. Okay, so let's constitute the Hamiltonian for this system. So the Hamiltonian for this system is equal to, we have to include the kinetic energy terms, right? We have to include the kinetic energy term. How to include the kinetic energy term? The kinetic energy operator is minus h square divided by 8 pi square m. Right here we are talking about the kinetic energy of the nucleus, so I give capital M. Okay, and minus h square divided by 8 pi square m. And where is m? Where m is the mass of the nucleus. Which nucleus? I don't know. We have n nuclei, and I am specifically talking about the ith nucleus, so that is why I give mi. So mi is the mass of the ith nucleus. Then del I square, that is the Laplacian operator for the ith nucleus. Okay, so that is the kinetic energy operator for the ith nucleus. But in total we have n nuclei, so we have to write n terms like this. From we have to give I is equal to 1, 2, 3, etc. to n. Then only we can write the kinetic energy operator for all the n nuclei present in our new system. Okay, so in order to do that, I just add the sigma symbol here. Sigma I is equal to 1 to n. Okay, then I can cover all the n nuclei. So this is sigma minus sigma I is equal to 1 to n h square divided by 8 pi square mi. That I square represents the kinetic energy operator for all the nuclei. Now I have to talk about the kinetic energy of the electrons. Okay, so how can I write it? Again, minus h square divided by 8 pi square m. Okay, here m is the mass of the electron. I don't need to write mi or mj or anything, etc., because all electrons in the system have the same mass. Electron's mass is a constant. But the nucleus may be different depending upon which nucleus it is, but it is electron here, so we don't need to talk about the mass of the electron specifically for each electron. Okay, so I'll just write here minus h square divided by 8 pi square m del j square. That is a Laplacian operator for the jth electron. Laplacian operator for the jth electron. So I have p electrons in total. So I have to do this for all the p electrons. So for that I include the sigma sign here. Sigma j is equal to 1 to p. Then it will cover all the p electrons. So I have the kinetic energy operator for the p electrons in the system. Okay. Plus. Now we have to include the potential energy terms. First, let us include the potential energy due to the nucleus repulsion. Then we have to include the kinetic energy due to the kinetic energy due to the nucleus electron attraction. Then we have to use the kinetic the potential energy due to the electron repulsion. So we have to include 3 more terms in order to accommodate all these kinds of interactions. Okay, so putting all these terms together, let me write it as V R R. V R R. You will understand why I have given R and R here, because it depends upon both nuclear coordinates and electronic coordinates. That's why I have given VRR here, and I am going to define what is VRR here. Here VRR VRR is equal to, it is the the first term in the VRR is due to the potential energy due to the nucleus repulsion. Since it is a repulsive potential energy, we have to give the plus sign. So we are considering two nuclei. The one nuclei has the atomic number Zk, that is a kth nucleus, atomic number of the kth nucleus. And then we are considering the interaction of this kth nucleus with the lth nucleus. Okay, the atomic number of the lth nucleus is Zl. Okay, so what is a charge then? The atomic number multiplied by the elementary charge of the proton. That is a charge, right? Then Zk into Zl into E, that is the charge of the proton in both Zk and Zl. Zk into E into Zl into E, that is Zk Zl E square, that is the product of the charges of the two nuclei divided by the distance between the two nuclei. That is, since it is the distance between two nuclei, I give capital R. Okay, then distance between kth nucleus and the lth nucleus, that's why I am giving RKL. Then we have to consider the distance between any two nuclei in the system, right? Then we have to add the sigma sign here, sigma, okay, K, sigma K. The K can have any value because we have how many nuclei we have? We have n nuclei. So sigma, the K should talk about the interaction of all the nuclei with the next nucleus. But there is one thing that you have to remember here. We have given here K and L in these terms. But K and L, for example, you can consider then K is equal to 1. Then we are talking, that is the kth first nucleus. Then we are talking about the interaction of this first nucleus with all other nucleus. So L can be 2, 3, 4, 5, etc. to n, right? Then we are talking about the interaction of the second nucleus. Then K become 2. Then we have to talk about the interaction of the second nucleus with all other nucleus. Then interaction of the second nucleus with 1, right? Interaction of second nucleus with 3, 4, 5, 6, etc. to n. But there is a problem that you have to understand here. See, this, if you are specifying 1 again here, actually that is a repetition, right? Because you have already spoken about the interaction of the first nucleus and second nucleus here itself. Like, see, here itself you have talked about that. Now, if you are again talking about the interaction of the second nucleus with the first nucleus, that is same. So it will be a repetition. Therefore, you should not include a K here when you are talking about the interaction of the one here when you are talking about the interaction of the nucleus 2 with other nucleus. So when we are talking about the interaction of the third nucleus with the other nucleus, you should not talk about 1 and 2 because 1 and 2 are already specified in the previous cases. Then you have to talk about 4, 5, 6, etc. to n, like that only, right? So that is why you have to give here one condition: K is less than L. K should always be less than L. If you are talking about 1, if you are taking 1, then 2, 3, 4, etc. If you are taking 2, then 3, 4, 5, etc. like that. So the L is always greater than K. So that is a condition that you have to impose there. Okay, I hope you understood that. Minus, okay, that is a nucleus repulsion. Now we have to talk about the attraction. How the attraction is originating? The attraction is due to the nucleus electron attraction. Okay, nucleus and electrons attract each other. So let us talk about the attraction of the kth nucleus with an electron. Okay, kth nucleus with the jth electron. So what is the charge of the kth nucleus? That is atomic number of the kth nucleus, that is Zk multiplied by E, that will be the charge of the kth nucleus, into the charge of the electron it attracts. That charge of the electron is also E, therefore Zk into E. Zk into E, so therefore Zk E square divided by the distance between the kth nucleus and the jth electron. I write it as Rjk. Rjk is the distance between the kth nucleus and the jth electron. Okay, so we have to consider all these type of terms, all these kinds of types of terms. So here, then also we have to apply the sigma sign here. Sigma, we have to count all the nuclei. That is nuclei k is equal to 1 to n. Then we will count all the nuclei in this term. Then we have to count all the electrons also. So we have to give a sigma sign, that is for the electron, that is j is equal to 1 to p. J is equal to 1 to p. Then it will count all the nuclei and all the electrons. Okay, plus last one is the repulsive potential energy due to electron repulsion. So that is E square, that is the charge of the electron multiplied by the charge of the other electron divided by the distance between the two electrons. Let me write it as Rmj. Okay, that is the distance between the mth electron and the jth electron, and we have to do this for all. Then again we have to apply a summation here. So m, but the condition is that then m is less than j. You know why it is like that. I have already defined this for the nucleus repulsion. The same is applied here also. So m is less than j is equal divided by r in j. So that is a Hamiltonian. That's a Hamiltonian for a system having n nuclei and the electrons. Let me put this Hamiltonian. This is equation number 1. Okay, this is equation number 1. And now you already understood all the terms there, right? Mi, the capital Mi. I hope you already understood. Capital Mi is the mass of the ith nucleus, and m is the mass of the electron. Del I represents the Laplacian operator for the nuclear coordinates, and del J represents the Laplacian operator for the electronic coordinates, and Zk is the atomic number of the kth nucleus, Zl is the atomic number of the lth nucleus, E is the charge of the electron or proton, RKL, capital RKL. Okay, capital RKL is this one. Capital RKL is the distance between the kth and the lth nuclei, and small rjk, this one, is the distance between the jth nucleus and the kth nucleus and the jth electron, and rmj is the distance between mth electron and jth electron. So you understood all the terms here. So we have a very big Hamiltonian operator here. So since we have this very big Hamiltonian operator here, let me quote the famous quantum chemist Ryan Levy. You already know this famous quantum chemist and author Ian Levy. Okay, he has a very famous quantum chemistry book, and you have to read that book. And I'm quoting him, Ian Levy, what he talked about this very big Hamiltonian. And in his words, this Hamiltonian is formidable enough to bring the terror or strike the terror in the heart of any quantum chemist. Okay, this Hamiltonian is formidable enough to strike the terror in the heart of any quantum chemist. Such a big Hamiltonian. with so many kinetic energy and so many potential energy terms. The kinetic energy of the nucleus, the kinetic energy of the electron, and then different kinds of potential energy terms of what a big Hamiltonian. And working with this Hamiltonian is going to make your life very terrible. Okay, so it's a problem. We have a very big Hamiltonian here, and it is going to give us very terrible nights and days. Okay, so somehow we have to simplify the calculations using this Hamiltonian. So that is the next task. Simplify. Sorry, simplify. That's what we are going to do next. Okay, so we have to simplify the calculations using this kinds of big Hamiltonian having the nucleus and electronic terms. That's a very important task. That is going to make our life easier if we simplify this. Okay, then let us uh, uh, examine this Hamiltonian before going for further simplifications. The first one is that the first term in this Hamiltonian is the nuclear kinetic energy operator. So let me write the first term here, nuclear kinetic energy operator. That is TN cap. Okay, N represents the nucleus, and it is in terms of R, that is nuclear coordinates, that is equal to what is a nuclear kinetic energy operator is Tn cap R is equal to minus sigma I is equal to 1 to n and h square divided by 8 pi square m h square divided by 8 pi square mi del I square. Okay, del I square, that is the uh, nuclear kinetic energy operator. Let me put this as 2, that is the nuclear kinetic energy operator. Then we have electronic kinetic energy operator, right? That is T cap electron. Okay, and the electronic kinetic energy operator is this one, which is the electronic kinetic energy operator, that is sigma j is equal to 1 to p h square divided by 8 pi square del j square. That is electronic kinetic energy operator, and that is equal to, that depends upon the electronic coordinates. Okay, and that is equal to minus sigma j is equal to 1 to p h square divided by 8 pi square m del j square. That is the electronic kinetic energy operator. Let me call this as equation number 3. Then we have VRR. It is already written there. VRR. Sorry. The screen is gone too low. Okay. So we have VRR is already defined there. So what is that? Where is that? Okay, now. Okay. Actually, I called the equation number 1 for this one. Okay, this is equation number 1. Okay, the equation for the Hamiltonian, and the VRR we already defined it next below that. Okay, so we already have VRR, that is the potential energy operator, and then the potential energy operator actually constitutes the 3 terms. You already know that. I don't need to go for further explanation of that. But certain things that you have to note here is that if you are writing the entire Hamiltonian H cap, the entire Hamiltonian H cap, the first part of that entire Hamiltonian is kinetic energy operator of the nucleus, that is Tn cap R, that is the kinetic energy operator of the nucleus. Then we have the kinetic energy operator for the electron. Okay, kinetic energy operator for the electron, and plus we have VRR. R. Okay, but here we have to consider this kinetic energy of the electron plus VRR. That we have to consider in another way. So let me write it as T cap EL R plus VRR is equal to, what is that? That is minus sigma j is equal to 1 to p h square divided by 8 pi square m del j square, that is the T cap electronic. Okay, uh, then VRR, that is minus sigma this one minus sigma, we will include the first term is positive one, so plus sigma k less than L. Okay, you may be remembering, I can't show that in the screen itself, otherwise I cannot write it. Okay, so k less than L, then Zk such L E square such k such L E square divided by RKL minus, okay, let me write it down, just 1 minute, minus, okay, sigma k is equal to 1 to n, k is equal to 1 to n, and sigma j is equal to 1 to p, sigma j is equal to 1 to p, then Zk square divided by rjk plus sigma m less than j, e square divided by rmj, right? So we are keeping this out. Okay, such k is a del E square divided by RKL term out. Okay, then you consider all other terms, that is the kinetic energy part of the electron plus electron nucleus interaction plus electron interaction. This is all about electron, right? The first part is the first one. This one is about the kinetic energy of the electron. This deals with the potential energy, the attractive potential energy between electron and the nucleus, and this one deals with the repulsive potential energy between electron and electron. So this is all about electron, but this is about nucleus. This is about the nucleus. This is dealing with the potential energy due to the nucleus repulsion. Okay, so if you are adding the first, third and fourth term, we can call this as the purely electronic Hamiltonian. Okay, so we can write it as H cap electronic. So H cap electronic means the first term plus third term plus fourth term, that is H cap electronic, and that is RR, H cap electronic RR, because it is H cap electronic RR because it depends upon both the electronic and nuclear position coordinates, because it is talking about the electronic kinetic energy, then it is talking about the electron repulsive potential energy, then it is also talking about the electron nucleus attractive potential energy. So it is depending upon both the position coordinates of the electron and nucleus. So it is H cap electron RR plus the second term we can write it as VNN R. Okay, that is the potential energy due to the nucleus repulsion, that is VNNR. So you understand what is H cap electronic and VNNR, right? H cap electronic and VNNR. So H cap electronic is this one plus this one plus this one, that is H cap electronic, and VNN is this one. Okay, so let me write at least VNN here. So VNNR is equal to sigma k less than L is such k is such L E square divided by RKL. RKL. Okay. So we have analyzed the Hamiltonian for the system. The Hamiltonian for the system. Now we are now talking about how to solve the application of this Hamiltonian in simple terms, okay, or how to simplify the application of this Hamiltonian for the real systems. That's what we are going to do. And it is in this part we are going to take some important approximation, and that approximation is by Born and Oppenheimer. So I haven't said you what is Born Oppenheimer approximation. So I have given you only an introduction where the Born Oppenheimer has is where the Born Oppenheimer approximation is going to be applied. Okay, so it is applied in the case where we have a very big Hamiltonian having the nuclear and electronic parts. The nuclear kinetic energy, electronic kinetic energy, nucleus potential energy, electron nucleus potential, electron neutron potential, all these terms comes together and make our life very difficult. And at this juncture, we are going to introduce the Born Oppenheimer approximation, and that approximation I will tell in the next session. Otherwise, this video is going to be very lengthy and you will be super bored and you will throw this video out and you will not learn this. So I will tell you what is this Born Oppenheimer approximation and how this approximation will make the applications of the Hamiltonian simpler in the real systems. That is in the next class. Okay, thank you for watching.